Thanks for the introduction, and thanks a lot for inviting me. It's a pleasure to be here and to talk about some charge transfer. The concepts I will present are quite simple, so you will all understand it. But I want to start with something related. So most of the talk will be about molecules on surfaces, but I will start with actually metals on surfaces, metal nanoparticles, because it's quite beautiful. So what we see here is actually gold nano islands on a support. They are quite big, 700 atoms per island, and they are perfectly shaped. You see also some structure. This is a monolayer structure. But the really fascinating thing here is the shape, why they look like this on this support. This is magnesium oxide, and you would actually expect to have three-dimensional, somehow spherical particles on this support, but they are actually just one atomic layer high. So 700 atoms, perfectly hexagonal, one atomic layer high. They are on MgO, and the reason why they are like this, why they form these flakes, these nano islands, is because this MgO is quite thin. It's only 0.6 nanometers, and it's supported by silver. And this special sample system, or this support, magnesium oxide on silver, promotes charge transfer into the gold. And this charge transfer stabilizes this two-dimensional gold. Now, the nice thing, which is not so much related to the topic of the talk, is simply this. We see here STM conductance maps, where we probe, in principle, the electron density on the surface, and here you see indicated the bias voltage. So this is positive, means unoccupied states. And we see perfectly, well, very nice patterns, stationary states. So this islands is a perfect hexagonal two-dimensional quantum well, and what we see here are quantum well states. So basically, this is what you know from the introduction to quantum mechanics, particle in a box system. Well, we are probing here unoccupied states, and I told you before that we have electron transfer into these particles. So obviously, these are not the transferred electrons. So the question is, where are these electrons that are transferred? And you might think that, well, in these particles, these electrons are distributed. So I don't know how many electrons are transferred into the gold particles, but there will be tens of electrons, so strongly negatively charged. So we would first guess that we have these electrons somewhere in the interior of the islands, but you also know there is Pauli repulsion. Electrons don't like each other. So what they will do actually in these nano islands, and this is also something you can see in conductance maps here, they all go to the perimeter atoms, to the outer atoms of these gold islands. And you see also here some periodic structure. So there are so many electrons that they probably form delocalized states along this chain in the perimeter. Now you can also form these clusters that are not so perfectly hexagonal shaped, but more irregular shaped, and then you have more low coordinated sites. What you see here on this image then is this bulbs or these protrusions are these localized electrons that we have on the particle edges or particle low coordinated sites. And actually this will be my only reference to catalysis here. This can, of course, be used to drive some reactions. One thing that we studied already a couple of years ago was the interaction of CO2 with these nano islands. And actually, based on infrared spectroscopy, we concluded that CO2 actually gets reduced, so takes a charge and couples with another CO2 to form oxalate, C2O4. So they basically drive the CO2 coupling reaction. And just recently, we investigated this with STM again and could actually identify these the products. Actually, what you see here on this magnesium oxide surface, this is the molecular species that's present on the surface after CO2 interaction. And in comparison with infrared spectroscopy, we can identify this as an oxalate species on the surface. And you can do the test by simply heating up these clusters. They will form three-dimensional clusters, and they'll be not reactive anymore because they don't contain these charges anymore. If you do the test reaction with CO2, you don't see any new species on the surface. So actually, these 2D clusters, because of this charge transfer that is promoted by the substrate, are reactive and do some chemistry. Good. My last first introduction slide is this one. So consider you're a student, PhD student, prepare these samples. Here we put a bit more gold on, and you see what these two-dimensional islands get really big, and all islands are two-dimensional. Then your postdoc comes in, has more experience, does the same preparation, same parameters, takes an SDM image, then it looks like this. And then 1 day later, the professor comes, has even more experience, and does the same preparation, and the sample looks like this. So what we see here, I indicated here, I colored the two-dimensional ones and the three-dimensional ones. So the brighter ones, three-dimensional gold clusters. And of course, everybody has its own experience with preparation of ultra-thin films. For example, it takes different temperatures while preparation of different oxygen pressure. And actually, this could be the result then, that you basically go from completely two-dimensional gold clusters to almost entirely three-dimensional gold clusters. And the reason here why this happens is because the work function has changed of the substrate. So here we will have a low work function. Here we would have a high work function. That's the basic idea of what I'm going to tell you in the next 20 minutes, is by controlling charge transfer through work function tuning. And this is nothing, well, this is actually what we showed here. So high work function, less electrons can be transferred, less two-dimensional clusters can be stabilized. Good. Well, this would be the outline. I will tell you something about integer charge transfer, because what we've looked now is actually a system that is weakly interacting. Gold on magnesium oxide is typically weakly interacting. And also organic semiconductor molecules on oxide surfaces are typically weakly interacting. And for this, we can use this integer charge transfer model. Well, I'm going to tell you something about single integer charge transfer, so transferring a single electron, and then actually going to double integer charge transfer, which has not been observed so far, and doing the charge transfer in different directions, so from substrate to molecule, molecule to substrate. Good. Basics, and you all know this. We start with our thin film system. So we have a metal substrate, this would be silver. We have a magnesium oxide, which is an insulator. We have an ultra-thin film. And then we put a molecule with certain HOMO energies on top of it. And typically, if we bring them together, they are vacuum level aligned. And if electron affinity and ionization potential are such that the Fermi energy of the substrate is in between them, then we will have no charge transfer. So charge transfer can be induced, for example, if we reduce the work function of the substrate and shift the electron affinity level down below the Fermi energy, and then electrons will flow to the molecule. On the other side, if we increase the work function, the electron flow will be reversed. So the HOMO, which is filled, will give an electron up to the metal, to the Fermi level. Of course, here we have an insulating ultra-thin layer. This electron transfer process is electron tunneling. So depends, of course, then on the thickness of our ultra-thin layer. Good. One thing we have to consider here is if we talk about tunneling, then we always transfer a single electron. And this is actually the reason why this is called integer charge transfer. If we transfer a single electron, then we need to, of course, consider the spins here. 2 electrons go into an orbital. We transfer a single electron, so one electron will be in the occupied region. We form a so-called SOMO, a singly occupied molecular orbital. And the second electron will have some difficulties to go into that orbital because of Coulomb repulsion. The first electron doesn't let the second electron. Good. Now let's look also at our system. So we have a system consisting of a metal, a dielectric, and a semiconductor on top, and we have an electron transfer from metal, for example, to the semiconductor, to our molecule film. This can actually be viewed as a simple parallel plate capacitor. If we have electron transfer, We have negative charge outside, we will have an image charge in the metal, and of course this forms a dipole. And this is nothing else than a potential difference that we form between inner parts of metal and outer parts, the molecule film. And this potential difference is quite easy to calculate because, well, that's the parallel plate capacitor formula, and it depends on the number of charged molecules per area that we have, for example, here on the outer side. This potential difference is also similar to the work function change of the sample that is induced by adsorbing a molecular film, or a molecular monolayer. So we start with a substrate that is clean, that has a particular work function. If we then put the molecular film on top and have charge transfer, we have an additional dipole which changes the work function. So in this work function change, according to this equation, will then be proportional, if the system is ideal, with the number of charged molecules that we have on the surface. Good. There's very famous, well, this concept actually comes from organic electronics because this has been investigated for systems, organic polymers on metals that are typically used in organic electronic devices. And this measuring of the, or measurements of the work function changes has actually been quite powerful. And what we then typically observe, if we start with a certain substrate work function, measuring work function after putting the molecule on, is a behavior where actually the substrate work function or the work function change is zero. Then we're in the so-called Schottky-Mott limit, no charge transfer. And if the well, this then goes in two different directions. If we have charge transfer, we're in the Fermi level pinning regime, and the work function is constant in this Fermi level pinning regime. But this can be on either side of the vacuum level alignment. Here we would have charging of the molecule, and here we would have discharging of the molecule. Good. The question is now, can we look at this on a molecular scale? And we have tried this with our substrate, magnesium oxide. So few words on the preparation. We typically grow 3 monolayers of magnesium oxide on silver 001. Magnesium oxide is an insulator. It's a huge band gap of roughly 7-8 eV, also as a thin film. The reason why this is so interesting for us is because we can tune the work function of the substrate without changing the surface chemistry. This is important. And why does this? So here we have SDM images. On the top panel, we see the MgO morphology. So we probe here the conduction band of the magnesium oxide. Here we probe with SDM somewhere in the band gap. We are more sensitive to silver, not so much to MgO. Our typical preparation condition is this one here. So we form roughly 3 monolayer high islands. If we reduce the oxygen pressure, we see that the island morphology changes, but we see also some bright spots here in this SDM images. And this is additional magnesium. Magnesium basically ionizes on silver. Will get positively charged. We have a positive charge outside, negative inside. It will reduce the work function. And the work function that we measure here is actually 2.5 eV. The stoichiometric one is 3.1 eV. And if we oxidize this at a higher oxygen pressure, we go back to a normal morphology, and you see these dark spots here now appearing, and these dark spots are oxygen atoms at the magnesium oxide silver interface. And this leads to a work function increase, so 4.1. So we have a large range of work function that we can probe with this magnesium oxide thin films on silver, depending on our preparation conditions. And this is actually backed up by DFT calculations. So if we put, for example, magnesium into these substitutional sites on the silver, we get a work function of 2.1 eV. For our stoichiometric one, we get 3 eV. And if we put interstitial oxygen at silver, then we get 4 or even higher eV work function. And actually, this can be tuned quite continuously by just varying the preparation conditions, in this case, oxygen pressure. Good. Our first test on this was with an organic molecule, as I said before. pentacene, which is an organic semiconductor. And we put these pentacene molecules on our stoichiometric magnesium oxide surface, took STM in the filled states and the empty states, and you see, well, this is an orbital-like appearance, and the orbitals look similar in filled and empty states. This is already a good indication that we have charge transfer, because if we see the same orbital structure, this means that, well, we have basically a SOMO and a SUMO of similar origin. Single electron has been transferred. In this case, this is LUMO derived. So basically the pentacene is singly negatively charged. And we see this SOMO-SUMO gap also if we do a STS spectrum. So here we see the occupied LUMO, and here we have the unoccupied LUMO. And the Coulomb gap between them. Good. Now we go to photoemission. We see in photoemission, we see the same peak that we see in STS at the same energy. So this corresponds to the SOMO. And here now we did the work function variation. So we started at a very low work function, 2.3 eV, and increased the work function of magnesium oxide silver actually up to 4 eV. But you see is a gradual change, well, a gradual decrease of the intensity of this emission feature, of the SOMO feature. And the intensity is basically proportional to the number of charged molecules we have on the surface. So over a wide range of work functions, we gradually decrease or change the number of charged molecules in our system. You also see here that the position is constant, which means that we are in a Fermi level pinned region. So we did a lot of experiments here, a lot of parameters varied. At the end, we look at this work function plot that I showed you also in the beginning, and we can really get this vacuum level alignment regime where we have no charging at high work function, and then the Fermi level pinning regime at lower work functions. Now, quite important here is, well, common belief was, before we reported this, that once the system enters this Fermi level pinning regime, all molecules are charged. And actually, this is not the case. In our model, basically, once we enter this system, we charge one molecule. And then, of course, we have this parallel plate capacitor model. We need to increase the potential difference, so delta phi, the work function difference. So we then need to go to lower initial work functions to charge up more molecules until at a certain work function, low work function, we have charged up all the molecules. Good. So I think that's an important outcome. Is this also be detectable with STM? We didn't do too many experiments on this with STM, but here you see one preparation. We use a different molecule here, that's porphyrin. And this is a full monolayer of this porphyrin molecule on the magnesium oxide surface, and we see here some bright molecules, and actually these bright molecules are the uncharged molecules, all other molecules are the charged ones. So we actually can also detect this with scanning time spectroscopy. For the uncharged molecule, we see the LUMO above the Fermi surface, you see the LUMO appearance here. And for the charged molecules, we see the LUMO appearance below the surface, and here, well, this would be the SOMO, and here would be the SUMO. So we have the coexistence, actually, of charged and uncharged species, somehow similar to what I've shown you at the beginning with the gold clusters, that we have two-dimensional and three-dimensional clusters, charged and uncharged. Good. Now, you will find in the literature many studies on this organic electronics that show you this curve from here to here, but not beyond. No, most of the systems that have been investigated have seen single integer charge transfer, so only one electron transferred. Actually, it should also be possible to put a second electron into the orbital. And, well, we suggested that we should have a second Fermi level pinning regime, vacuum level alignment regime for the negatively charged ones, and then enter a Fermi level pinning regime for double charging. Well, with pentacene, we ended somewhere here. And you've seen the work function that we needed to actually fully charge all the molecules was 2.3 eV. So this is already quite low. So there are not many substrates that have a lower work function than 2 electron volts. So if we would like to go to double charging of these molecules, we would need to go to 1 eV work function substrate, which is not possible. But the other option is that we change something on the molecules. This charging depends not only on the work function of the substrate, but also on the electron affinity of the molecule. And we could simply choose a new molecule with a higher electron affinity than pentacene. And this is actually PDCDA that we took has an electron affinity of 3.9 eV in the gas phase, which is really high. And then we can do simply the same experiments. We did some STM. Before we have here, well, forms a nice monolayer. You see here the structure. It's called a T-type arrangement. And on these monolayer molecules, we perform scanning tunneling spectroscopy. And we see a huge gap around the Fermi level, which could either indicate it's non-charged, and then we would have a HOMO-LUMO gap, or it's actually doubly charged. Then we would have an occupied LUMO here, and here the LUMO plus 1. DFT calculations actually provide some support that this is doubly charged because the LUMO here is completely below the Fermi level, which would mean double charging. Well, is there some evidence? Well, first I should tell these STM images were taken at bias voltages here around the Fermi level in the gap region of the molecule, so we don't see any molecular appearance. But if we would go to bias voltages either here at -1 eV or plus 1.5 eV, we should see some orbital-like appearances, and this is actually what we do. So here, occupied region, this should correspond to the LUMO, to the occupied LUMO, and unoccupied region should correspond to the unoccupied LUMO plus 1 molecular orbital. Here are the representations of the gas phase orbitals, LUMO and LUMO plus 1, and actually you would have a hard time comparing this and saying this is the same. But of course, if we do STM simulations for the system supported on magnesium oxide, then we actually get very, very good agreement between simulations and the experimental STM images. So it seems that the PDCDA molecule is really double negatively charged on this substrate. What we can now do, again, perform UPS. UPS is somehow faster than STM. In UPS, we get again the same LUMO, occupied LUMO peak at the same energy than in STS. We also measure here the work function change. And the work function change, well, we start at 2.8 eV work function with the magnesium oxide. After putting the molecule on, the work function is 4 eV. A huge increase in work function. A positive change means charge transfer into the molecule. Then we do the tuning again, choose a work function which is quite high of the magnesium oxide, 4.2 eV. Look at the final work function is 4.8, and you see the work function difference is just half that of the one that we had before. Now, simple capacitor model, if the potential difference is 50% or just halved, then the number of charged molecules is, or the number of charges is simply half of that from before. So this means that we either have half of the amount of doubly charged and uncharged, or just the same amount of singly charged. And we can now probe by tuning the work function, this region between this extreme and this extreme. With UPS, we see a shift in the SOMO peak, not in the SOMO, in the occupied LUMO peak, and we do also the work function plot. And you see that we are far away from this Schottky-Mott limit, which indicates non-charged molecules. But we see something like a regime where the work function changes parallel to this Schottky-Mott limit, which looks like a vacuum level alignment regime. So I put the lines here to make identification a bit easier. We have 3 regimes here. The first regime is Fermi level pinning of the negatively charged molecules. So in this regime, we start
basically from uncharged molecules, start charging the molecules in the monolayer until all the molecules are charged. We have this SOMO-SUMO splitting. And now, once we are here, of course, it requires some energy to put another electron into the molecule, to the next affinity level. And this means vacuum level alignment. So as we decrease the work function, we shift this LUMO level towards the Fermi energy. And once we cross the SUMO level, or the SUMO level crosses the Fermi energy, we start doubly charging the molecules. And this happens then at this point. And here we again get to this Fermi level pinning regime where we then have the doubly charged PDCDA molecule. I think this shows quite nicely the concept and easy physics. Basically, in a parallel plate capacitor model, we transfer a single charge. Good. I have 2 more minutes, which is fine. 3 more minutes. 4 more minutes. Okay. Perfectly in time. Then we go actually to the other side of the diagram, actually making, well, transferring a charge or an electron from the molecule to the substrate. Also, this you find also something in literature, basically from device people who investigate this, but actually I didn't find any molecular level study on this. And we tried to get some STM, molecular scale STM data on this. Here, we would need to go to a very high work function. So with magnesium oxide, we could tune up to 4.5 eV. We tried iron oxides. We have some limited tunability with actually this monolayer FeO film on platinum, because it has this moire structure, and you get basically a potential difference on the different positions of the moire of about 26 eV. But we found that our molecules on iron oxide are not charged. So this 5.5 eV work function is not sufficient to actually discharge our molecules, but we found then one substrate with a really high work function. This is molybdenum oxide, a thin film on palladium 100, 6.7 eV work function. I don't want to talk too much about molybdenum oxide. It's an important oxide for several reasons. We could prepare this monolayer molybdenum oxide. Actually, my colleague Samu Surnev did this. And it has one advantage, high work function. Disadvantage is it's completely oxygen terminated. It has molecular groups that stick out, so it's very unreactive. There will not be much interaction with molecules. And one disadvantage are these anti-phase domain boundaries that we have here. And of course, they can alter the adsorption properties quite a bit. Good. We tried phthalocyanine, which is shown here, organic semiconductor, on this molecule and on the surface, and did these experiments at liquid nitrogen temperature. And actually, the interaction is really weak, so that most of the molecules, they are found here at step edges or at this antiphase domain boundaries. They are flat, which is good. But if we increase the coverage, then we see the transformation into an upright standing monolayer, which is not good for us, for STM, because for the upright standing molecules, we won't be able to identify some molecular orbital shapes that would give us some idea about the charge state. So maybe the molecules would stay flat if we go to lower temperatures. Liquid helium temperatures would be a possibility, but we thought there must be another way to make them flat, namely by confinement, where they stand up because well, molecules meet each other and then they form a standing phase, but the standing phase, of course, needs neighbors. A molecule needs neighbors to stand up. So if we could confine these molecules, we might have the chance to keep them flat. And this is what we tried. So we have these antiphase domain boundaries. Pentacene, you know already from the study at the beginning, is this elongated molecule. We deposit this and decorated our antiphase domain boundaries with these pentacene molecules. And then put the phthalocyanine in. And we were hoping that Now, due to limited mobility, they would stay in these pockets here. And actually they do, but this looks quite crowded. But if we zoom in, then you see these molecules, individual double signing molecules here in these squares made up by these pentacene molecules that decorate the interface domain boundaries. And here we already have an indication that we have single integer charge transfer, because what we see here at positive bias, empty states, is a molecular orbital appearance that corresponds to the HOMO of the gas phase. So if the HOMO is above the Fermi level, it means it has lost an electron. DFT basically confirms this. DFT also puts for both the upright and the flat molecules the HOMO at the Fermi energy, meaning that we have Fermi level pinning here, so single integer charge transfer can be expected because we have a weakly interacting substrate, and our STS data also confirm this. So if we take STS data on top of these molecules, we see some sumo gap, which is quite small for the upright molecules, for the standing ones, but big for the flat ones. The difference is here screening. So the standing ones, they're quite close to each other. We have intermolecular interaction or intermolecular electron screening, which reduces the gap, the sumo gap, quite a bit. For the flat ones, they are unscreened because they are lying on this oxide surface. So we get a huge sumo gap. Good. And I'm at the end, good in time. So I think what we can summarize is that we have now molecular level control and also, of course, insights into these integer charge transfer processes on weakly interacting substrates, in our case, oxide substrates, but you can do this, of course, with any two-dimensional material like graphene or HBN or whatever. Thank you very much.